Hi, everyone. My name is Bethany Scott, and I am the Digital Projects Coordinator at the University of Houston Libraries. I'm going to be talking today about the process of assessing and ultimately improving our electricity consumption for our digital preservation activities. So I'll start off by giving a little bit of background about digital preservation at UH. So our first digital preservation policy was drafted and approved in 2014 to 2015. And we started using Archivematica in production in 2018 for our preservation storage. We now have nearly 5,000 packages at about 30 terabytes in storage. The content that we have stored in Archivematica is almost all digitized material created by the UH Library's digitization unit for our online access repositories. We also have quite a bit of film and video content, which was done through outside vendors. And of course, that accounts for some of the largest file sizes in storage. But despite making some progress with just even setting up our digital preservation program, until recently, we had not yet considered the long-term sustainability of the program from an environmental standpoint. To address this, I gathered information on our technology infrastructure and its energy expenditures, and I evaluated the requirements of our digital preservation policy to identify areas where the overall sustainability of the program may be improved in the future by modifying our current practices. So there are three components to the carbon footprint analysis that I conducted. First, I did an inventory of the hardware and equipment used for digital preservation activities. Then I calculated the electricity used by the local equipment. And finally, I investigated offsite storage providers' sustainability policies and practices. And I actually recently wrote a couple of blog posts for the Society of American Archivists electronic record section that goes over the hardware inventory and the electricity calculation. It goes into a lot of detail there. I will give a quick summary right now, and that way we can spend more time on the offsite storage providers in this presentation. But if you would like to read about the electricity consumption estimation, please check out the blog posts. They're linked here. Part 1 is available at bit.ly/ERSPOST1. And part 2 is available at bit.ly/ERSPOST2. So my first step on understanding our carbon footprint was to get an idea of the components of the local infrastructure that support digital preservation at UH. So I worked with our system administrator to figure out what pieces of equipment are used for processing, storage, networking, and other elements of the overall digital preservation program. We came up with this inventory. So from the inventory list, we looked at the technical documentation for the specific hardware components to determine the likely maximum power consumption for the hardware. We also estimated the power draw while idle, and then a range of partial power draw scenarios in between. So here are the findings. As you can see, the estimated maximum greenhouse gas emissions derived from power use for the digital preservation hardware is around 124,000 pounds annually. That equates to 56.3 metric tons. So that is the greenhouse gas emissions from our digital access and preservation hardware annually. To put this in perspective, it's equivalent to the greenhouse gas emissions from about 140,000 miles driven by an average passenger vehicle. It's also equivalent to the carbon dioxide emissions from over 62,000 pounds of coal burned. Now, this is just an estimate for the time being, but when we are able to go back to work on campus, I am planning to get some actual power draw numbers directly from the equipment in the server room to continue this research. And I'll talk more about that in a little bit. But of course, this energy use only accounts for our local storage. So we also have to account for offsite storage, which would be another factor in an organization's overall carbon footprint. As we all know, lots of institutions' digital preservation policies require them to keep multiple copies of their digital assets in different geographic locations. And there are several offsite storage providers that we can use to address those requirements. The big three commercial providers are Amazon, AWS, Google Cloud, and Microsoft Azure. And then there are also non-commercial providers from the cultural heritage sector, such as Chronopolis at UC San Diego and the Meta Archive Cooperative, which is supported by the Educopia Institute. Since the cultural heritage options were created by and for digital preservation practitioners, there tends to be a bit more transparency about their standards and procedures, and there could be additional services that they provide, such as geographic distribution built in as well. And also, the cultural heritage options tend to be hosted out of higher ed institutions, many of which are already moving towards carbon neutral sources of energy on campus, and which have a lot of documentation about their sustainability practices at the campus level. So for example, Chronopolis is hosted out of UC San Diego, and data in the Chronopolis network is also replicated at the University of Maryland Institute for Advanced Computer Studies, and also the Texas Digital Library. Each of these institutions employ sustainability officers and have stated commitments and action plans to move towards carbon neutrality in the coming years. For instance, UC San Diego is committed to reducing its energy use intensity on campus and obtaining 100% clean electricity on campus by 2025. Not too far off. Regarding the commercial providers, all three have also taken actions to reduce their carbon footprint, some more effective than others. As an entire company, Microsoft has been carbon neutral since 2012, and in fact, I believe they are now carbon negative, actually. Google is carbon neutral too, which they achieved through improving the energy efficiency of their data centers and through constructing or purchasing renewable energy sources. And Google actually provides a fair amount of transparency too, through their annual sustainability and environmental reports that they release every year. And then that leaves Amazon. Unfortunately, Amazon remains one of the least transparent companies in the world in terms of environmental performance, but it is by far the biggest provider, which is demonstrated on this chart. So this is visualizing the power consumption for data service providers in Virginia, where the Amazon US East region is located. This is the core of the AWS global infrastructure. As you can see from the chart, Amazon consumes 3 times more electricity as the next highest service provider. And actually, Amazon's power demands in Virginia increased by 60% between 2017 and 2019, but they did not add any new renewable energy. So as a result, the data centers in Virginia are only 12% renewable powered. And this is in pretty stark contrast to their stated commitment to be 100% renewable powered by 2040. And in an open letter from September 2019, Amazon Employees for Climate Justice highlighted their complaints about the company's performance, citing the intensive use of fossil fuels throughout the business, polluting communities, actively helping oil and gas companies accelerate extraction of new reserves, and funding climate denying think tanks and 68 members of Congress who voted against climate legislation 100% of the time. Now, some of us may have to use AWS for backups due to its low cost. I know we fall into that category. So I want to give a little silver lining here. There are 5 AWS regions that they have stated to be carbon neutral already, including the US West in Oregon and 2 regions in Europe. So if you have to use AWS, you could consider choosing one of the carbon neutral regions if you are setting up your AWS storage for the first time. Or you could switch from US East to US West as an example. So as I mentioned before, there are some additional things that I would like to research further regarding our carbon footprint and how we might be able to reduce it over time. First off, along with our digitization unit, I am looking into a tiered approach to selecting appropriate preservation file formats. So for example, we might choose a high-res full-color TIFF as the preservation master for an object like a medieval manuscript, where researchers need to investigate the minute details in the parchment, texture, the ink and decoration, and so on. But for something like a folder of 20th century typed correspondence, where the value is more informational rather than artifactual, we could decide that a lower resolution file or even a PDF is sufficient. This would reduce the amount of storage space, therefore allowing us to digitize more content at the same level of energy used for storage. Also, when we get back to work on campus, I would like to capture actual point-in-time power consumption figures from our local hardware infrastructure. And then I'd like to look at whether we can reduce our power consumption by changing our preservation processes. So as an example, when we do resource-intensive actions or computations, like a fixity check, does that actually cause our power consumption to go up significantly? And if so, what is the balance between an appropriate schedule of fixity checking to confirm the integrity of our files, while also ensuring that our carbon footprint and our energy use doesn't spike too much? So finally, to wrap up, here are a couple of ideas about what you can do if you're interested in these issues. First off, contact your sustainability office. Many institutions of higher ed have a sustainability office and a team who's already working on this, who can provide information on current and future sustainability efforts going on at your institution. They also may be able to provide you with insights on the sources of electricity on campus. So even if your campus is not yet 100% renewable powered, there might be portions of the grid that are. You might be able to encourage renewable energy sources for buildings where your local storage infrastructure is housed. And finally, for AWS users, there is a free tool called Green Cost Explorer, which provides a breakdown of what percentage of your AWS service is green or carbon neutral versus not carbon neutral. And so this could give you some insights into whether your use of AWS is carbon heavy and where you might be able to improve by switching to different region or service of AWS. All right. Well, thank you very much for your attention. I look forward to chatting about it with y'all on Slack. And if you have any additional questions or feedback on this at a later date, please feel free to email me anytime. My email address is bscott3@uh.edu. Thanks again.